start with theoretical calculations. That's the way things always come out. So I just make these jokes up, and sort of jokes about the Nernst equation and why he did it that way. And, you know, I don't know, when you went to school, one of the things in your book list was the 5-place log table. Make sure you carry it to class on days when you want to do something with precision. Okay. And your slide rule. Now you carry these fancy things. They do twice as much as any of those. And then we just throw this in. So that's the Nernst equation. And we use that for non-standard state cell potential. And in order to use it, and that's why I put this problem up here, here's the Nernst equation problem. Whoops, sorry. I keep looking at that one. This is the one that I went to first. Because this is also a Nernst equation problem, and the big difference we saw from the earlier problems, non-standard state concentrations. And so what we have to do, and notice I put these questions in this sequence. Sometimes I just say write the spontaneous equation for the reaction in the cell, things of that sort. Let me put some more questions in. It says calculate Ecell and how you put with that. Well, not always. I did in this case, obviously. Write the equation for spontaneous reaction. Now, as I said when I was talking about the Nernst equation a long time ago, possibly so long you forgot about it, I said in order to do a Nernst equation problem, you have to have a balanced chemical equation, and you have to have the E0 cell that goes with it. And that's the problem we did a few minutes ago where I just showed you I wanted to have a positive E0 cell, and so I took the large minus the small. The second, third equation, problem here, which is problem B. So you want to write the equation for the spontaneous reaction. And I am allergic to this building. My nose is going to run all week, and as soon as I get in here and start lecturing, my nose runs. What is this room?
So number 3 would be the third equation?
Number 3 is what he asked right there.
Okay.
Write the equation for the spontaneous. I just added this extra one where I said write the equation occurring in spontaneous standard states. Because sometimes, and by the way, if this stays the same, don't write same. I want you to rewrite the equation again.
Okay.
Okay? Don't just say same as in B. I want to see an equation again. Yes?
When you're writing your equations on the board, I noticed you're not using state symbols. Do we not need to do that unless it's a gas?
Oh, you mean like here?
Yeah.
Well, if you have 0.175 molar, I guess you could talk about the molarity of a gas, but we usually don't. So this must imply that you got this ion by dissolving it in an aqueous solution.
So it's
In
implied.
other words, yeah, you can't make, if you're doing mass spectrometry, you can make the U3 plus ion, if you can find it.
But like the solid, you don't have anything.
Oh, you mean for this end?
Yeah, all of them.
Well, these have to be what? Solids, because that's the electrode phase. You can't, like, remember I made the joke, you can't clip into a solution. You have to clip onto them. You have to hook your wires onto something that is metallic.
Okay. It's just also when you're writing out your spontaneous reactions, the net, I noticed you're not using any state symbols. I just want to know if we should be adding them or not. Like, go up towards number 1, just underneath. Okay, down, further down. That, like right there, I don't see any state symbols.
Okay, well this, what would you say? These are the solids. The vanadium and the nickel are solids.
Yeah, I understand that. I'm just saying, it's okay not to put state symbols.
Oh, you mean you want to put... Some books will do that. It's not wrong, but the only way you can have these elements is in the solid phase. In other words, we're working at 298. So one of the comments I made to my MD student when we were doing thermochemistry, one of the things about working at 298, which is room temperature, you know there are only 2 liquids in the periodic table, there are only 3 gases, everything else is solid. When you have something like this, you can't just have this, or you can't just have H+, you have to have an anion to go with it somewhere. But these are net ionic equations, so spectator anions are missing. So here you could have, what? For this one, you could have 4H2SO4 for this one. Then over here you'd have Ni2, NiSO4 for that. So if we're doing molecular, you just have to put in the spectator. But when we're doing equilibrium and everything else, we don't do it for molecular equations. We always do it for net ionic equations, unless it's the gas phase. In other words, the gas phase reaction, then you can have molecules reacting. H2 plus I2 gives you 2HI gas. Then you do molecular. Okay? But once you get into aqueous solutions, you don't put in the spectator ions. Yes?
So when we write our equations on our exams, do we need to or not?
You may if you want, just don't do it wrong. And the only way you can have these ions would be what? Can't read it, it says AQ for aqueous. And one of the textbooks out there does that consistently. So when he has an equation like this, it takes up 2.5 lines because he keeps putting in aqueous and solid and everything else. And by the time you get done going to the end of the equation, you forgot where you started. So I mostly leave out the aqueous because that's the only way you can generate these ions. This, I didn't put the solid because the elements are solids at 298.
But like in a standard hydrogen electrode, you have to denote that H2 is a gas, correct?
Right.
That one you have to.
Yeah, when I wrote the half cell for the standard hydrogen, I'll write it this way this time. Gas, oops, what did I forget?
Bar.
1 bar pressure. Notice I didn't put down anything other, and activity of 1 is what your book frequently uses. But notice this specifically has to be HCl. If you want it to be in more detail, if you use sulfuric acid, that would not be the standard hydrogen electrode because it would be a slightly different potential with 0. So there are certain specifics in there, but this is what we write for short. And if you wrote this, which we did just a minute ago, this is the diatomic gas. It might be soluble in water, but not very soluble because you collect hydrogen over water. So you wouldn't think of that as an aqueous solution. But it's not wrong. If you want to say 2H plus, aqueous, 2 electrons, H2 gas, that's certainly not wrong. But I'm not going to look for that. Because as you notice, I didn't write it down when I was doing it because there's just so many things you can write down in an hour or whatever time you have. So it's not wrong to put that all in. A lot of times for short, you just get rid of it. And there are some textbooks, as I say, where they do put all that in. And it just makes the equations twice as long, and you get bogged down. Most people skip over the words aqueous, gas, and everything else, and they just look at the chemicals in the first place. Okay, so coming back to this, let me finish writing out all the things. Write out delta G0 for the reaction into 5, calculate delta G. Now what's the difference between this and this? Well, this is the standard state, but the cell I gave you right here was non-standard state. So when you want to calculate the equation I had up here a few minutes ago, and this could be for the reaction, so I'll say cell here. I said we could do it for half reactions, but all that happens is if I'm doing it without the if I'm doing it in non-standard states, then I'm using the non-standard state cell potential. Okay. Because sometimes I'll ask this question on a quiz, other times I'll ask this, and somebody always asks, did you forget to put the 0 there? And I said, no, I want to answer the question I wrote. Okay? So I didn't forget to put the 0. In other words, 0 means, the superscript 0 means standard state. This means non-standard state. And here we're just, and the reason I wanted you to write separate reactions, because this might be one reaction, this might be reversed. In other words, they're not going to be completely different. They're either, it's going to be going to the left or from the right to the left. In other words, you're writing forward direction, reverse direction, or they could both be forward direction. It depends on the numbers I put in the problem. Okay? And that's one of the reasons I said I don't follow the rule where the book always says put the reduction on the right-hand side, because that's one of the things you have to calculate from the problem. This may or may not be the reduction half cell in this particular cell.
So then you'd be asking for delta G, not delta G0.
I could ask for either one, and I'm going to ask for either one. Right there, I wrote the 2 questions. Okay.
But if you were asking for delta G0, wouldn't it have to be written in standard form?
No. All we have is this equation right here. This we use E0 cell. This we use the non-standard state cell potential. Let me go through and do the problem.
Okay, that'll probably be helpful.
Let me get some numbers up there. Let's see if I can get something that writes a little darker here. So first of all, I'm going to do this thing. Here's my cell. I'm just going to write over everything. All I'm doing is copying what's there. And up here, whoops, I think when I turn off the lights so you can read everything, you won't be able to read it. So it says, okay, now I'm going to turn off the lights so you can see what this was some old days a few minutes ago. So there are the 2 pieces of data I gave you. Here's the cell I gave you. And I said I want to start doing all these calculations. To calculate E0 cell, I have to use the Nernst equation. And I'm going to use this one because that's what I'm used to using. Because I have a button on my calculator, like I said. It's easier to find my LN button these days. Okay, so the first thing I'm going to do, I need to have this because I need the balanced chemical equation that goes with it. This is standard states, and the table of data is given at standard states. It says up top somewhere. Because you don't tabulate non-standard state data, you calculate it. So what I said is you want to take larger minus the small. Sure enough, it came out positive. And it came out positive for this reaction, where this is now written as the oxidation path reaction. So I'm going to write, and you do a lot of them, you can take shortcuts, but my advice to you is don't, so you don't confuse yourself, because I confuse myself if I take too many shortcuts. And the other one I don't change, because I left it like that. Lowest common multiple, 6. So I'm multiplying this by 3, this by 2. So I have and this would be my answer for number 2. There's my answer. Make sure I wrote it where it says write that equation. I always leave you those spaces, so I'd expect to see that equation appear there. Because that's what happens at standard state spontaneously. Now the next thing is, I want to calculate Ecell. Notice I have to go through all of this before I can even start calculating Ecell. So now I'm going to say Ecell. E0, oh, I have the equation up there, so I don't have the equation. I just got done calculating here. Minus if I do this right, I don't have quite enough space. Okay. As I have to erase it. So what I have to do is look at this. And notice I don't put these in because they're the solids. That's why there's no charge or anything else. I guess they could be liquid if I were working at really high temperatures, and I could dip an inert electrode into the liquid. I don't know what they do at really high temperatures. They liquefy, but then they probably do something strange. I don't know. Okay, so this is the setup. And a lot of people like to use this number. As I said, the important thing is make sure you show me what n is, because I look for that. And then U3 plus, there it is, 0.4 squared over that's 0.02 cubed. And the way you want to do that, mathematically speaking, multiply these things out, take the log, and then continue multiplying, adding, and subtracting. Sort of started from the back and work towards the front.
N's always the lowest common multiple?
Yeah, it's
Okay.
total n is not the lowest common multiple. It's the number of electrons gained and the number of electrons balanced, and the number of electrons lost in the balanced equation,
Okay.
which you get by taking the lowest common multiple. Right. So I guess that might be the short way to say it, but the correct way is to always say it's the number of electrons lost, which is the same as the number of electrons gained, assuming you balance the equation correctly.
Okay.
And balanced equation never has electrons in it. Half reactions do, balanced equations don't. Okay. Let's see if my calculator works okay today. Monday mornings are hardly ever works, right? Because you have to push the right buttons like this. Well, with my glasses on, that might make it easier. always write this part down here. Not, I mean, you could just go ahead and put the answer there in your quiz, but the reason I write this is I wanted to talk about something that's happened here. 0424. Notice this cell potential, when I get done calculating it, came out to be plus 0.0576. But you see it's decreasing. Eventually I can change these numbers enough that this would be a negative number when I calculate it. Remember, he showed you that graph with the delta G where it went across from positive to negative as the concentrations changed in the last chapter. Same thing happens here. It's getting smaller. If I make this number bigger and this number smaller, eventually I'll be subtracting a number that at the absolute value will be bigger than this, and I'll come up with a negative one. But since I came up with a positive sign here, for number B, I already said there's what I would write for number 2. Number 3 I would write. So, as I said, make sure you write the equation again. Then I can answer the next questions. I'll do number 4 here.
Dr. Denver, I have a question.
Yeah.
For number 2, why did you choose to reverse the U instead of the SR equation?
Right here, remember when I took the larger minus the smaller, the thing I subtracted means I changed the sign here, right?
Okay.
And if I change the sign, it means I reverse the equation.
Gotcha. Thank you.
And you always want to keep that in mind when you're doing that because, like I said, one of the most common mistakes people make is they'll reverse the equation and they'll change the sign and then they subtract again and then they change the sign one more time. Yes?
So if the Ecell actually ended up being a negative number, we would flip
This
number
equation
3
would have been
would have
reversed.
flipped.
And then the Ecell would be a positive number.
But it's pretty safe to say, you're saying that E standard cells are always going to be positive numbers.
At standard state because well, one of the problems I did give you in here, remember a few minutes ago I gave you the non-spontaneous reaction. And the E0, and the way you designate that, you'd say minus something or other volts, because that's not what Ecell is. It's a number you calculated because you have to start with an equation, and the equation you started with was the non-spontaneous equation.